Alright, my trucks. My invented trucks. Alright, these have car fender overhaul wheels. There's truck pads, like, we're gonna hide that. Hide, hide this. Alright, the brakes, they work in a box on a rack pinion rod. So, the rack and pinion rod, just keep that in mind that there's a shaft connected to this back part, which is it's a cylinder. It's a cylinder for grease, like hydraulic oil. The hydraulic oil pumps goes through the center, and then it goes and pushes on the edges of it, like passes in between the walls. So let me show you the trimetric view of the truck. It has two auxiliary reservoirs. Usually the reservoir tank is somewhere on the rail car, but now they're on the truck. And then underneath it, we have the rack and pinion rods for the trucks and the brakes, and they go into a electric motor, where the oil is passed from this side wall through this sweep path into the cylinder and then back through the shaft into the middle. So we basically have each side of the truck has its own reservoir and its own braking pinion. The brakes are centered in the side. They have the regular shoe hairpin so they can be easily removed. And now let's look at 2-degree. This shows the pressure relief valves on the sides, angle cock overhead angle, the brake cylinders themselves, some ABW brakes on each side of the truck. So this is like each square is over here. A1 is controlled by A1, A2, B2, B1. Each have an AB valve and springs and cylinders. It kind of looks like that, but in SolidWorks, and the truck's a little bit different. So what we're going to look at now is a flip-flop circuit, flip-flop air electrical circuit for auxiliary reservoirs on trucks and of the rail car, which is brake rodless. This system is brake rodless. So we'll start on the corner. We have a auxiliary reservoir, which is on one side of the. Remember, it's on the truck, so there's two of them. But an ABW valve, which is usually a passenger car brake, which applies in the three valves positions for relapse, charge, and exhaust. So we have a one-way valve, which is usually your brake cylinder, but and it's also solenoided and on a rack. Here's a pressure relief regulator valve, which allows us to change the pressure into the side of each different side of the truck. In the truck, we have an electrical circuit, which is a flip-flop circuit, an oscillator, which does step down, sinusoidal, and step rate and step function, step rate function. So flip-flops are computers or transducers to tell how much pressure and voltage, the electrical voltage pressure is going into the solenoid. So they can be regulated by the pressure regulator. Alright, there's a battery that controls the traction motor, which is in the center of the trucks. Also ported to the cylinders. The cylinders on each side, it has some ports to the traction motor, polarize that. They have a communication field, which is usually running the traction motor, which should be probably over here instead, because I just finished my SolidWorks before I redid this drawing. In the middle, we have a cross rate, this arrow to arrow, and it's an adjustable resistor to the amount of transduction. This adjustable variable from your pressure regulator to the transducer for the oscillation of your trucks. So we have a battery, which is just going to power it individually. These little circle lines right here, this circle to this circle, controls the pressure regulator system by an electrical current to each car. If not, it will run on a battery by itself, which has a flip-flop logical certificate. The pressure relief valves over here on the side is to dump the air on either side of the car. Then again, it has two angle cocks for front and reverse. Alright, so the ABDXW valve, one way usually is a brake cylinder on a regular, so we're just going to say it's a brake cylinder 1. And so what's going to happen is 1 to 3, 2 to 3, or it's going to go, it's kind of like rotating wheels across that crossways, which is the outer dotted line, which will follow open path. What we want to do here is make each side, we're going to make it each act like it's its own truck, like it's its own car. This whole auxiliary ABW section, one car. Then it would be connect, like if it was coupled to the next car over here, and 3 and 4, otherwise it doesn't work. Let's talk some physics. What we have in mind keep in mind, let me drag this over and share it on this. I like Windows with this flap circuit. Okay, we have to remember the offset as the set load changes, the proportional band and measurement range. Let's start with there's going to be a time lag and there's dead time too. So let's between the front of the train and the rear of the train, we have a brake application with a CFM, which is usually 60. And a regular 60 cubic feet a minute is on the test. So we have EX or exhaust, normal direct exhaust, HP or high pressure retaining 20 pounds air and brake cylinder. And your slow direct exhaust air brake cylinder is at 60 to 90 psi. Now let's say each auxiliary reservoir has 25 cubic inches of or 10.5 gallons. Equalizer reservoir 35 or 100 cubic inches, 5.5 gallons. Brake cylinder has 630 cubic inches, 2.7. The brake pipe is 1/4 inch pipe. Crossover brake pipe is 1 inch. Brake cylinder is air reservoir system and a variable. That's how that works. And speed control will be used in the oscillations, which is in this little thing right here. And transducer records the oscillations and the pressure dropout. So you have oscillation between the cylinder and the application brake output. Option 1, variable control. We're going to have the... Alright, let me recenter this. Option 1, variable control. The variable lead angle cock and the trail angle cock. So in between the car, we have to have the same amount of air going from the same, say this was not a regular car, for the regular train has on its angle cock and angle cock in the front and also in the back here. So the angle cock in the front and the rear have to trail. It's not until you start building big trains that there's any differential. An emergency brake application is 35 to 20 psi percent of the auxiliary reservoir into the brake cylinder. So the auxiliary reservoir, this is just in a 1 pound auxiliary reservoir is 4 times the brake service if the reserve is 1 pound and 2.5 of the brake cylinder. So what we're getting is 1 pound of the auxiliary reserve pressures onto the brake cylinder at 2.5. So our pressure regulating devices right here need to be set to the brake pipe pressure for 1 pound of pipe or in the auxiliary, so we can keep the same numbers and adjustable variables, this gives us our adjustable variable between our cross flow. This little square box right here in the dash, that's your cross flow, which makes it go like your rotating wheels of a car. First service auxiliary reservoir is 1.2. A normal train length works at 900 feet per second. The brakes apply at 500 feet per second. 500 feet over 50 feet a car length of air. Train emergency brake pipe is always greater than auxiliary reservoir pressure, so there's got to be more brake pipe pressure than the auxiliary reservoir. Brake production is 1.5 times to 2 inches auxiliary reservoir. So, and what is recharging? Less brake pipe cylinder pressures the auxiliary reservoir. That's when the brakes recharge. Less brake cylinder in the pressure than in the auxiliary reservoir. So this right here, the little solenoid arrow one-way valve has less brake pipe cylinder than the auxiliary reservoir. Alright, a deadband is a range of variable input without response, which also comes into play with how long the train length is and in between cars. Flow control, minimum car, brake air hose, end of the trail, and control way three-way valve. The control three-way valve is usually this. It shows like if you have your what is it? It's a main equalizing application, initial release, or independent application. Alright, you have input, train brake pressure, lead the trail car. So the train brake pressure and leading the trail car have to be within brakes the same. To work this train schematic, this whole truck and brake schematic with electrical has to operate in any in between, at the front and at the rear of the car blocks. Okay, it might need some choking with a 24RL, 24R26 because they each have different. They have different step positions on the automatic brake control, unit control, automatic brake alarm, function control, brake recharge. Manipulated variables that we have to consider: minimum release, initial reduction, full surface suppression, bail off, independent bail off, and processes. We have air brake train test, train control, locomotive control, and end of train device. End of train device is the primary feedback from front to after to the rear. We have three position valves: A, B, W, and reserve. They're usually on passenger trains, which they have a button that comes out on the side to show you if the brakes are applied. So, alright, resident flow, reserve charge capacity, full main reservoir. 8 brake application of 20 psi or a minimum 6.8 psi results in a car length to the end of the train. And 1 psi is usually putting about 2.5 inches of the stroke on the brake cylinder. So we have 1.5 to 3 inch psi brake charge rate, airflow, minute, dead time, capacity, reservoir, volume, capacity, reservoir, brake cylinder, weight, tonnage, and electrical. So we have to use the pressure regulator once again and this transducer to make sure and then there's hysterias. Back to the brake point cylinder, and then this part right here. Let me show if I can hide this. Alright, that hid too much. Anyways, well, now I'm screwed on that for looking back at that, as I can't. It'll take me more than a minute. Your oscillations inside will step or ramp, self-regulation, process frequencies. We have to make sure these brake cylinders have a release, relap, and a charge. You gain response rate and time constant by brake cylinder, brake pipe, and auxiliary reservoir. So that makes a lap when they're all the same, like nothing's happening. Step function differential lap between processors, load change, variable oscillation, four-way supply, supplied to drain in the brake, offset. I'm gonna open that again. Alright, it has to have a 6 to 8 point PSI return and a class 3 airflow lead between and in between the rear of the car. Why not the locomotive? Let's see. The locomotive has traction motors and a dynamic braking system, so it's sort of like a dynamic braking system, but it's only flipping it on and off in a cross-way fashion. The brakes being applied, sort of like ABS, like it's doing it, oscillating the brake cross flow in an open loop. Alright, to reset, the auxiliary has to equal the brake pipe, so what's ever going in the angle cock have to equal what's in this auxiliary reserve on the side. Balance and compilation, input, production, element, results, output, primary feed-in, actual signal. That signal will be given by the transducer. You have gain process, and then reset rates. Reset equals response over the time. The rate, increment, speeds, and criteria set forth. Flow rate. Once again, we're looking at airflow method and 80 psi strong at the rear of the train and in between, like As long as the pressure remains constant between the flow rate and the pour area are linear. So once again, there was a 6.8 psi reduction, and that made a 2 pound 3.3 like application of the brakes in poundage. And we have our over here. We have our value pressure to drop across the bank. And lastly, we have our tank capacity, maximum, minimum, limit, and gallons interchanges between the valves. And I had more notes, but I lost my rocket book. So I hope I didn't mention the motor, but the motor is inside this flip-flop circuit for the traction motor, which would flip on and off the traction motor. So basically, it's kind of like ABS, depending on how you ramp or step function or oscillate, how often it turns on the brakes. And then we'll look at the truck one more time. Alright, so there's our rack. This is our electric trans-solenoid solenoid. But like in this rack, it pushes fluid out and goes back in, and then it comes out this shaft into this. And we have our auxiliary reservoirs. And then the only thing that's missing really here is ABW. So we have a flip-flop circuit, alternating brake, electric solenoid brake pin, auxiliary reservoirs, and a brake. We've now made the truck brake rodless, so it will work just basically on an air pipe instead of linkage. There's no linkage to it. It just works with an air pipe. Like all you have to have is the air hose, and that's that. This is my trucks.